It's my pleasure to welcome you all to the third International Faculty Development Program on Advanced Functional Materials, Energy, Environment and Sustainable Development organized by the Department of Physics in association with Department of Mechanical Engineering. It is my honor to welcome the chief guest of the day, Chief Director, Honorable Principal, Vice Principal, HODs, all the faculty members, and research scholars from various institutions and internal to this wonderful event. As we come together today, we celebrate the pursuit of knowledge, the thrill of discovery, and the passion for understanding the fundamental laws of our universe. From the intricate dance of subatomic particles to the majestic sweep of cosmic evolution, science seeks to unravel the mysteries of existence. As we set out on this intellectual journey, we hope that the session will offer all attendees a plethora of insights, enable fruitful interactions, and inspire fresh perspectives about the topic at hand.
The curtain rises on our event. Let's get this program started. We are thrilled to invite the head of Department Physics and our convener, Dr. B. Seduraman, to deliver the welcome address. Get ready to be inspired and energized for the exciting sessions ahead. May I request your presence, sir?
Very good morning, distinguished Chief Guest, Chief Director, Principal, Vice Principal, Heads, Faculty members, invited speakers, and dear participants. A warm morning to all. It's my great honor and privilege to welcome you all to the third International Faculty Development Program on Advanced Functional Materials, Energy, Environment, and Sustainable Development. This prestigious event, organized by the Department of Physics in association with the Department of Mechanical Engineering, signifies our unwavering commitment to advancing knowledge and fostering innovation in these critical fields. We are privileged to have a Professor V. Subramanian from IIT Madras. His extensive contribution to the field of physics make him an ideal choice to kick off our event with his profound insights. Welcome, sir. We are fortunate to have our Chief Director, SRF Group of Institution, Chennai, Ramapuram and Trichy campus, for sharing his insights to the participants on the significance of this program and its impact on the academic community. Welcome, sir. I'm honored to welcome our principal. Your support and encouragement have been instrumental in making this event possible. Welcome, sir.
Thank you.
My warm greetings and welcome to all of our heads, faculty members of our group of institution. I also extend my warm greetings to all of our invited speakers. We will be enriched by insights and expertise of distinguished speakers hailing from various reputed institutions across the globe who will undoubtedly inspire and enlighten us. I'm delighted to extend a warm welcome to the participants who have joined us in this academic exchange. Your presence here underscores your dedication to pushing the boundaries of science and technology. I encourage each one of you to actively engage in this discussion, share your valuable insights, and seize this opportunity to learn from one another. I wish you all a successful and enriching program. Thank you.
Thank you, sir. The influence of a good leader can never go unnoticed. To start this event, we have with us a forward thinking individual, Dr. N. Seduraman, Chief Director, SRM Group of Institutions, Ramapuram, Chennai, and Trichy campus, a visionary leader who has guided us to new heights of excellence. He has been an inspiration to all of us and worked tirelessly to create a positive and supportive learning environment. As we look forward to illuminating insights, let's extend a warm welcome to Dr. N. Seduraman to give the presidential address. Sir, please.
Okay. Thank you. Good morning to everyone present on this happy occasion. Distinguished Chief Guest, Professor Subramaniam from IIT of Chennai, Principal Dr. Sivakumar, Convener, my namesake Dr. Setharaman, all the participants from globally participate, and my colleagues from ERP Engineering College, other kids. As you know, SRM is known for its innovative ideas, research act. ERP Engineering College, I could easily recollect when it was started. I was the registrar of SRM University at that time. I played my role on the direction of the chancellor. Today, I'm happy that the Department of Physics, in collaboration with Department of Mechanical Engineering, TRP, Trichy, organizing third International Faculty Development Program. Topic is very interesting and important on advanced functional materials, energy, environment, and we all know we organize FDP, conference, workshop in order to strengthen, in order to provide more information, more knowledge about the latest development. It may be technology, it may be energy, it may be environment. Professor Subramanian sir, we are very much careful and we are taking all possible efforts, particularly for sustainable development in Trichy campus. You might have come to Ramaram campus. I don't know whether you have gone to Trichy campus or not. You are welcome, sir. My principal and his colleagues will take this opportunity to invite you to Trichy also for some important discussion. Now coming to this FDP, any program, as I told you, organized to enhance the knowledge. Trichy is, though middle of the state, it's the college is located in a surrounding area of, almost all villages. It is on the highways, but in and around the college, we have so many villages. Our faculty and students, they are taking their best, they are doing their best to develop, to help the villages. Now, definitely, the participants from other parts of the country will make use of this opportunity. I am told they have got very good number of papers. It is going to be presented in this conference in 2 days. Definitely, it will throw light on it. And I only request TRT faculty to send all the papers and get the comment. Though you have got judges and all, choose papers as per the direction of Professor Subramaniam and get issues, take it forward. It may be useful to the students. Just merely discussing and leaving the matter as it is will not help for the growth of the institution, for the growth of the department. Any knowledge that should be shared, any knowledge, any idea, innovative ideas you get in this, that should be developed further, that should be taken it forward. I hope you will do it. Thank you for having given me this opportunity to share this. Sorry, my dear participants, I am traveling. I am not in Trichy. Usually, I go to Trichy on every Thursday and Friday. This time, unfortunately, I have some other work in Chennai. I am not able to go there in person. I am happy that I am able to participate. I am able to all the faces who are going to present the papers in this third world conference. Thank you, thank you, thank you. Over.
Your encouragement has given us the boost to create more unforgettable events in SRM campus, sir. Thanks for being our event evangelist, sir. With great gratitude and admiration, I would like to invite the guiding light of our SRM TRP Engineering College, our Honorable Principal, to felicitate the clustered spectators. He is a great academician and a phenomenal leader affiliated with SRM Group of institutions. Your commitment to excellence is an inspiration to many of us. You have been a pillar of strength to this institution, sir. May I request your presence, sir?
Yes, yes, madam. Thank you, madam. Respected Chief Guest, Dr. V. Subramanian, sir. Good morning, sir. our beloved Chief Director, sir, very good morning, and other dignitaries, and then speakers, organizer, and faculty members, and dear participant. Once again, a very good morning to one and all. So it's my privilege and honor to extend my warm felicitation to the organizer, speakers, and attendees of the international online 1 week faculty development program on advanced functional material, energy, environment, and sustainable development, an integrational approach. Since this FDP is organized by physics department and the mechanical department, we made as an integrational approach. So at a time when the world is striving for sustainable solution to global changes, the theme of this FDP holds great significance. The development and application of advanced functional material are at the core of scientific and technological advancement in energy, environment conservation, and sustainable development. These materials have the potential to revolutionary industries from renewable energy to eco-friendly manufacturing and contribute to a cleaner and a green future. I extend my appreciation to the Department of Physics and Department of Mechanical Engineering for their collaborative work in organizing this event, bringing together experts from diverse domains, fosters an interdisciplinary approach, encouraging innovation and knowledge exchange. The participation of distinguished researchers and academics from around the world will undoubtedly provide valuable insight and inspire new research direction. To all the participants, I encourage you to engage actively in the session, interact with the expert, and explore new perspective that can enhance your research and teaching methodologies. Initiatives like this FDP are crucial in equipping faculty member with the latest knowledge, ultimately benefiting students and future researchers. Once again, my heartfelt congratulations to the organizer for their dedication and efforts in making this event a success. I wish this FDP a grand success and hope it leads to meaningful collaboration and impactful research in the field of functional material for energy, environment, and sustainability. Thank you.
Thank you, sir.
Thank you.
It's time to ignite the spark of knowledge. As we dive deeper into the program, with great honor, I invite the convener of the program, Dr. K. Shakti Pandi, Professor, Department of Physics, who stands as the beacon of this event, to brief to us about the faculty development program on this special day. Sir, please.
Good morning, one and all. Distinguished Chief Guest, Chief Director, Principal, Vice Principal, Heads of the Department, esteemed faculty members, invited speakers, and dear participants. With the grace of Almighty, it is my privilege to present a few keywords of this third International FDP Development Program on Advanced Functional Materials, Energy, Environment, and Sustainable Development. This is the prestigious event organized by the Department of Physics in association with the Department of Mechanical Engineering. This is our third series of FDP. The theme of this FDP is Energy, Environment, and Sustainable Development, aligns closely with the global mission of building a sustainable future. It serves a call to action for all of us to leverage the science and technology in developing the solution that are both innovative and environmental responsibly. Over the next 5 days, we are honored to host 14 distinguished speakers from renowned institutions across the world. These experts will share their insights on the advanced functional material across their diverse field, introducing at us cutting-edge research, empowering trends, and the novel applications. Their contributions will undoubtedly deepen our understanding and inspire the new directions of the academic and the research endeavors. Each day, the FDP program will have the feature of 2 technical sessions covering the fundamental and advanced aspect of the fundamental of functional materials. Additionally, we have arranged a special session focusing on material characterization technique, a crucial aspect of the material science. These sections will provide the valuable insights into the characterization tools and their industrial application, bridging the gap between the academic and industry. We are delighted to have more than 225 participants from various institutions and industry across India, notably 65% of the participants have already completed their doctoral degree, highlighting this depth of expertise present in the forum. Moreover, 38% of participants are women, underscoring the growing representation of women in science and technology. Our participants come across from the diverse background, including the professor, associate professor, assistant professor, research scholar, PDS, lecturers, industrial person, PG assistants, and education consultants. With such a distinguished gathering of the scholars and the professionals, we are confident that this FDP will serve as an enriching platform for the knowledge and exchange, fostering the collaboration and inspiring the groundbreaking the research in the field of functional materials. We are all know the National Science Day is celebrated on today, 28th February, to honor C.V. Raman's 1928 discovery of Raman effect. The theme for the 2025 is empowering the Indian youth for global leadership in the science and innovation for Viksit Bharat. We are all hope that this FDP will help further align with the theme. I extend my best wishes to all the participants for a productive and intellectual and stimulating FDP. Let us make that most of this opportunity to learn, share, and contribute the advancement of the science and technology for the sustainable future. Thank you.
Thank you, sir. The moment we have all been waiting for is here. Dr. K. Venkatesan, Assistant Professor, Department of Physics, will now introduce the chief guest who will spark new ideas and enthusiasm. So please.
Thank you. Good morning to everyone who are all gathered here. It's my welcome to all of the participants to our third International Faculty Development Program on Advanced Functional Materials, Energy, Environmental and Sustainable Development 2025. It's my pleasure to introduce our chief guest, Dr. V. Subramaniam sir, who has graciously accepted our invitation to join us today. He has completed his bachelor degree in 86 at St. John's College, Palayam Kotai, and completed 88 PG in American College, Madurai. Has completed his doctoral degree at 1995, Indian Institute of Technology, Madras, in the title of Microwave Conductivity Studies in some Semiconductors. And also, he has worked as a project associate at IIT Madras in 1995, and also 1997 work under the CSIR India on the development of non-contact microwave technique for the characterization of various semiconducting materials and devices, with a special interest on solar cells under the Department of Physics at IIT Madras, Chennai. Dr. V. Subramaniam joined in the microwave laboratory as assistant professor in 1988. It was established during the 1960s with the professor of Jayendra Shobhanadri as a head of the microwave laboratory. Has fully fledged microwave test benches with a German assistance. The microwave test benches for the frequency spectrum of 50 to 70 GHz were installed. These test benches have helped to produce more than 25 PhD and numerous MSc, MTech students, project students. The lab has also published over 100 research papers in the referred journals and equal number of in the conferences also. Now, Dr. V. Subramaniam sir is heading the laboratory. He has played a key role on the national exams such as NEET, and he also acted as a chairman for the GATE exam. He has delivered more than 80 plus specially invited lectures around the world, has completed 20 funded projects by various government agencies such as DST SERB, DRDO, DRNS, IIT Madras, Institute of Excellence. Once again, I would like to welcome Dr. V. Subramaniam sir to honor a chief guest. Sir, please.
Thank you, Professor Tyson. Chief Director, Professor Setraman, Principal, Professor Shivakumar, and conveners, Professor Shakti Pandi and Chitraman, and the head of the departments of Physics and Mechanical Engineering. Good morning, everyone. Good morning, sir.
Good morning, sir.
Yeah, I'm very happy to be involved in this faculty development program. This title is a very interesting one. Advanced functional materials with a special mention on energy, environment, and sustainable development. Nowadays, people do not simply say that I develop a material. Material, no, it should have not only one function, but the need for multifunctionality comes into the fore. So in this particular aspect, people are very much working on this advanced functional materials. I'm very happy that Dr. Shruti Pandey has actually initiated this particular series of FDPs, okay, helping the faculty, other research scholars. FTP programs, in general, is very helpful to the faculty and other people, mainly because it gives them a very great update on the recent research activity. Most of the times, faculty will be involved in the teaching, and then it's very difficult for them to spend time on the latest research activities. So these type of FTPs, STPs, etc., will be very much helpful in their growth as well as in shaping their research careers. When they go back to the college, they will be able to inculcate knowledge, to the students and then motivate them further on. And this particular FTP is also very special to me, mainly because the convener is Professor Shakti Pandey. We got acquaintance only through such a FTP program in 2018. Okay. So that way, I am very much happy. Whenever people attend this FTP, we always try to see how their future is going to be. Right? So it is not only simply making an FTP and then asking others to join or delivering a lecture, etc. It's not only enough. But as Professor Sitharaman pointed out, the Chief Director, one should be able to take it forward further. And in that way, I'm very happy that Professor Sakti is actually growing in that particular category. Okay? So I'm very much thankful to him for being acquainted with us during 2018. Another one is this is another jewel, we can say that, okay, or another important aspect of this particular FTP is the involvement of foreign faculty and foreign experts. Generally, FTPs and other things, they are being taken internationally, and also because of the most of the times it is going to be of the offline program. Okay, so people only from the near region will be able to attend. But this FTP, this international FTP on the online platform, actually has attracted many people all over the India. Not only that, we are also getting experts from abroad. So I'm very happy about that. Now, as I mentioned that material science is now expanding exponentially with a large number of avenues, coming from theoretical as well as experimental point of view. Nowadays, people are using this artificial intelligence and data science to improve further on their material characteristics. So one will be able to work on this material science not only experimentally, but also one can work on that in the theoretical aspect. If you see the special mention, or you can see that the course, the FTP focuses on energy, environment, and sustainable development with a large number of, or you can say that presently the world is dependent on the fossil fuel. One should be able to take it away from that, so that the sustainable development also will be in tune with that of the energy concept. So the energy, whenever we need it, okay, with the new functional materials, one will be able to work on energy harvesting like that of the perovskite solar cells you are having. Then you are having triboelectric nano generators, which are giving you the energy, magnetoelectric materials giving the energy harvesting. Several other things are there. But whenever you are working for the energy harvesting or energy area, well, there will be always an element of problem, we can say that, on the environment. Environment is suitably getting trouble. So one should be able to see whether we are able to get the energy from by actually disturbing very little amount about the environment. Like the case of now, you want to dry a cloth, you don't need to have a dryer. We can actually use the sunlight to dry. That's what our old people, our earlier forefathers are doing it. But nowadays, with the growth of the multi-story building, we do not have that particular opportunity. But these type of smaller additions to that will be able to increase or improve our environment and sustainable development. Okay, so I'm sure that this week-long FDP will go into this particular direction and help not only the teaching community but also research scholars as well. Okay. So, once again, I admire the management of SRM Trichy for supporting the coordinators in this particular effort. And the series, the third series, this now, and the series is the third one, and that's, how they are organizing. This is able to tell that the SRM Trichy is actively supporting them in all their efforts. My wishes to you all for the successful conduct of the FTP, and then once again, I thank the conveners and then SRM for inviting me to deliver this particular chief guest address. Thank you.
Thank you, sir, for your inspiring insights. Your contribution as a chief guest to this event is invaluable, and we are so grateful to have had you as a part of it. Thank you so much, sir, for accepting our invitation in spite of your busy schedule and making this inaugural event a grand success. Thank you. Now, we are moving on to the next part. The session 1 of the Faculty Development Program is about to begin. It's time to get to know our esteemed speaker for session 1, Dr. Tirthagiri Jayaraman. In a world where curiosity meets innovation, it is our pleasure to welcome our distinguished speaker, Dr. Tirthagiri Jayaraman, Academic Research Professor, Brainpool Fellow in Department of Chemistry, Gyeongsang National University, Republic of Korea. His current research is focused on the development of electrocatalysts for the production of energy-saving fuel and value-added chemicals. Dr. Tirthagiri has published 185 refereed papers in high-impact international journals, edited 3 books for Elsevier and RSC, 11 book chapters, and 4 patents. He has delivered several keynote lectures at international conferences and academic institutions. We are privileged to have such an influential person among us. Now, I gladly hand over the session to Dr. Tirthagiri Jayaraman. Sir, please.
Yeah, thank you, ma'am. Can you hear me?
Yes,
Yes,
sir.
sir, we can hear.
Yeah, thank you. Thank you for your nice introduction. Let me share my slides. Yeah. Shall we start?
Yes, sir.
Okay. So, good morning to all. Thank you for your nice introduction about me. So, myself, Dr. Tirthagiri Jayaraman, currently working as a research professor in the Department of Chemistry, Gyeongsang National University, South Korea. So, thank you once again for this opportunity, Professor Sakti Pandi, for inviting me to deliver a lecture. So, I am planning to share some of my research experience on the title of pulsed laser technologies in electrocatalysis. So, especially when we hear the word about pulsed laser, we can call it as like a pulsed laser deposition or laser irradiation or ablation. So laser deposition mostly on the solid gas-based reactions, but here in my research mostly focusing on the pulsed laser irradiation ablation in a liquid medium. So that how help for the synthesis of electrocatalysis and their applications. That's what main focus of this topic. So I am here in South Korea, here the city called as Jinju. Sorry, I'm getting one call. Sorry, actually, I didn't have any disturbance here in my system. Maybe you can check from your side.
Okay, sir. Now it's clear. You can continue.
Yeah, sure. So now currently I'm in South Korea, the city called as Jinju. It is in the southern part of the South Korea. So you are in Trichy, I mean SRM University. So happy to meet you all in virtually. So before going into the research talk, let me introduce about Gyeongsang National University and South Korea, I mean the Jinju city. So this is aerial view of Gyeongsang National University, the main campus, Gajua campus. So currently I am residing here in the BN80 building on the 7th floor. So this is the BN80 building picture. On this top of floor, I am sitting in this room 708. This is my office. So this is in front of our lab. So our lab is a core facility lab. So since we have a huge number of major facility, research facility, which I can show you in the next slide. So and also we call it as a LP lab. So laser spectro, I mean photochemistry lab, because mostly our synthesis of nanomaterial using the laser technique and their application towards the energy and the environment. So this is the campus beautiful view in the middle of like autumn season. So in the middle of summer and winter there will be a season. So this picture is taken in our university. Yeah. So I shared some of Jinju city pestle. I mean, what is the pestle in Jinju? So as I mentioned, our university located in Jinju. So this is the Jinju Latin Festival. In the month of every year, October, we celebrate a Latin festival. Almost 10 million people gathered at a time, and they will celebrate this festival. So some of picture is shown here. This is the Jinju character emo, and shown here some of Korean traditional food. So definitely, if you have a chance to visit South Korea, you definitely love this food if you are a non-vegetarian. So of course, there is a limited food for the vegetarian. Maybe you can love this Korean traditional food. So I can have a 1 minute clip about the university. So this is I mean about the university as well as about our lab. So 133 department. We have like 5 campus. So I am in Gajua campus, main campus. This is our lab actually. Yeah, this is the corridor. The earlier slide I shown here. This is our PhD student. So this is the BNIT building where I am sitting. So this is our lab student, our laser room, our ACM. So this is the main entrance of our campus. So this is our BNIT building. Like I am sitting here in this 7th floor core facility, like here almost is my room. Okay, so our core facility, laser spectroscopy laboratory, which majorly like almost 30 major instruments available. Some are listed here. Laser room, where mostly we synthesize the materials, and SEM, XPS, ICP for elemental analysis, AFM, GCMOS, Raman, rheometer, XRD, and so on. So thermogravimetric and other technique, levitator. So this levitator is especially used for the droplet system. So in general, what we do is bulk reactions. Of course, when compared to chemical synthesis, there is a huge advantage of laser synthesis that I am going to focus in the next slide. But when we are talking about the levitator droplet system, the reactant, for example, the chemical A plus B chemicals in a droplet system, you will keep in the middle of the levitator. Upon the node antinode, due to the ultrasonic levitator wave, it can be plot in the middle of levitator in this system. So there we can pass the laser or any heat chemical, energy to convert material synthesis as well as application we can monitor. So what is the beauty of this technique means, like before going for the bulk reaction, we can study the mechanism and also how the transformation takes place in the chemical reactions. For example, one metal state to another, another state, or any A plus B conversion, chemical conversion, everything can be studied via in situ spectroscopy, like PL, XRD we don't have, PL, FTIR, and UV, which we have connected in situ techniques. So of course, Raman, we have in situ Raman, but in future maybe we are planning for the XAS, which we huge funding the government has, like Korea government science center for XAS technique, like a table technique. So probably within 2 months we are expecting that will be installed in our lab. So with this introduction, let us move about the subject, not exactly subject. One slide I want to show like historical overview, why we need to study about the nanoscience. Let us say in 1980s we studied a major, of course it may be a two basics. Let us have 1 minute, like in a different way. You might have most of you professors are much experienced than me, but let me have in my own version. So in 1980s we studied a different subject, the major subjects so called, like microelectronics, physics, chemistry, materials, and microbiology. When the latest in the 2000s we studied a separate branch called nanoscience and nanotechnology. What is the beauty of this nanotechnology? Why this advancement is needed for the research? The best example is a energy storage device. So if I am right, my 10th standard or 12th standard, we have a DVD or CVD to watch movie or whatever, storage our even of course the research data. So we used the CVD and disk, the one big size plate. So currently, like almost the 10 years, currently we are using like a pen drive. The size has been much reduced, and the simultaneously density has been increased. So this is also a advancement of science, nanoscience. This is the beauty of the science. What is this beauty means? Everything, it is in a pen drive, we can carry out in a pocket, like thousands of one capacity of one disk. The storage CD or DVD can be stored in a single small size pen drive. That is the beauty of the science. So another example, we studied in 1946, we used a calculator which occupy the big room size, numerical calculator. By means of scientific advancement, finally it reached the handset, like a small handset called as a mobile. It can do everything. It attracted all the category of people, the rich people to like poor people. But the thing is, irrespective of the categories, like even of course the animals also started listening music, or whatever, the kids much more addicted to the mobile, cartoons and YouTubes, everything. All the things humans need, everything in a pocket. So thing is, it can order the food also, but only thing is we need to eat. That is the thing what we have to do at present. Everything we can order from my room itself. So this is also a scientific advancement. This is the beauty of nanosciences. So let us move to the our research topic. So in our lab, as I mentioned, we mainly focused on the pulse laser technique, especially pulse laser irradiation and ablation for the synthesis of various functional material. Once we synthesize and we go for the characterization as usual, then the application mainly focusing on the electrochemistry, energy, environment, and sensor. So we have like 30 group members. There will be a team, like I am one of the team leader. Under me, some 2 PhD and 3 master students are working currently. So my research area is mainly focusing on the energy conversion, like production of hydrogen and value-added chemicals. So for example, nitrate, which is a pollutant, we can convert into ammonia. So these kind of works I am mainly focusing currently. So recently I started with the PET plastic conversion into value-added product. So that was my current topic which I am focusing. So if you want to know more about laser technique, how these involved in the lasers, material synthesis, of course towards the application, you can refer this research article published in Nature journal, like Light Science and Application 2022. So this work has been awarded as a best paper in 2023 from this journal. So you can download and refer. You can know the fundamentals about the laser technique. So today I will focus about the electrocatalytic hydrogen production via water splitting. So that is what I am going to highlight in this presentation. So what are advantages of hydrogen? I mean, when compared to the other fossil fuels. So this hydrogen fuel used as a energy in the transportation, fuel production, industry, and feedstock. For example, feedstock in the ammonia synthesis, ammonia which is used as a fertilizer in agriculture industry. There are various techniques available for the synthesis of or production of hydrogen, but still this electrocatalytic hydrogen production technique, this process is called as a green chemistry process. Why it is called as a green chemistry process? So we know water which consists of H2O2. When it electrochemically split, the oxygen evolved at the anode part and hydrogen evolved at the cathode part. Any electrolyzer or electrochemical device which consists of two opposite reaction, two electrode system like anode and cathode. There will be a oxidation at the anode and reduction at the cathode. So you can ask a question. So if I am only interested on the hydrogen production, can I work like HER reaction or OER reaction? The research topic mainly focusing, if you go through the research article, some people they are like termed as a water splitting or water electrolyzer or HER, OER or ORR. So these are the opposite reactions. Why we call it as opposite reaction and how we can differentiate. So for example, as I mentioned, our topic is hydrogen production. Whether can I focus only hydrogen production? Yes, I can focus, because it is a opposite reaction which mainly depends on the potential. So thermodynamic potential, every opposite reaction it has own theoretical potential. For example, hydrogen evolution takes place at 0 volt in reversible hydrogen electrode scale. So oxygen evolution takes place 1.23. So overall reaction, even water splitting reaction takes place at 1.23, because the cell voltage is anodic minus cathodic potential. So these are the some basic things. So now the thing is, when we work like even if you want to go for basic things, when we call it as a opposite reaction, where we have to use a reference electrode. So we can term as a working electrode, reference electrode, and counter electrode. But all the material which we are working, mostly we are using as a working electrode based on the potential which we apply or which we scan. This can be act as a working electrode, act as a anode as well as cathode. For example, if I run the positive potential, the reaction it act as a mostly oxidation reaction, and the negative potential reduction reaction. So for example, in one of the reaction I have shown in this study is hydrogen oxidation reaction, that theoretical potential is minus 0.3 volt. It is a negative scale. Can it call how can we call it as a oxidation reaction? Why can't be it as a reduction reaction? Means, so the simplified way is the forwardic reaction solve is called as a oxidation reaction, and backward reaction, everything is a reduction reaction. So what is the backward and forward? Means that all the reaction will start and goes up towards up in a electrochemical CV, profile, cyclic voltammetric profile. So it will come, the backward means it goes towards the down. That can be the reduction reaction like OER or HER. These are all backward reactions. So when we talk about a full cell or device, where we call, there will be a two reaction. One is HER and OER. So the advantage of hydrogen I mentioned here, and what is the advantage of OER? You can mention like this oxygen naturally we are getting from the tree. So why we need to focus about the OER, or still why the researcher are focusing on OER means definitely this answer you might be known by this time, because of the COVID time, in especially in Tamil Nadu, without oxygen cylinder so many deaths happened. So this is because of the lack of oxygen cylinder, and we don't know, the due to the pollution and everything, we don't know in future. Of course, we started buying water I mean, we pay and drink the water, and in future we may also carry the oxygen cylinder. I mean, we will the market, they will sell the pure oxygen cylinder like this. We can carry in. Of course, we don't know in future anything. Everything is a prediction. We can't predict the nature. That is the I mean, crucial and bad thing, worry things. So here I mentioned the overall, I mean, optional reactions, HER and OER and overall water splitting reaction. So I don't want to go in deeper. So as I mentioned, this topic is especially hydrogen production is mainly in this device is mainly depends on the electrocatalyst, electrode material or electrocatalyst, which is used for the fabrication of anode and cathode electrodes. So these electrocatalysts, how we are synthesizing and what are the technique which we use, that is the research topic which we are focusing. So the overall performance mainly depends on the electrocatalyst used in the electrode material. Before selection, so in a research topic we need to plan before proceeding, whether for example it should be focused by these four topic, like improve the activity. Activity means electrocatalytic activity towards HER and OER and stability. Any device, electrochemical device, it is basically evaluated by means of the stability, because for example, the mobile phone, how much charge it has a battery. It is also electrochemical device which has a anode and cathode both reaction, and how long it lasting that charging. That is what mean by the stability. So it is always important. And the selectivity, when I am talking about the either you want HER or OER, so one material, it can be act as a both HER active or OER active, or some material is only a HER active. It is not necessary that the all electrocatalyst is active for both OER and HER. So selectivity is important, which is your target reactions. So investment on the operational cost to any research should be a which is reduce the cost wise and increase the lifetime, which is also the stability, and avoid the pollution. As I mentioned, this is the water splitting is a green chemical process. So similarly, the synthetic route also should be the eco-friendly or green chemical process must be adopted. In my research, I adopted a pulse laser technique, especially two technique: pulse laser ablation, pulse laser irradiation in liquid process to synthesize the various electrocatalysts. These electrocatalysts used as a used to fabricate on any electrode support, material, like electrode substrate, for example carbon cloth or nickel foam, whatever we can use it based on our requirement and selectivity of our substrate. So this material I am synthesizing using a laser technique. So what are the difference between the ablation and the irradiation, since I am using a two technique? Of course, the in the forthcoming slides we can see visually what is the difference, but to know in a very short, this ablation technique is a top-down approach, bulk material to the fragment, and irradiation is a bottom-up approach, small metal ion to the nanostructures. So there are various advantages which we can see in the next slide. For example, simple and clean and eco-friendly by no byproduct. These, if I say, you may not understand, but when you see in the next slide, you can easily understand. So these are the some video clips which we taken our lab for the production irradiation and ablation technique, like gold particle synthesis, like silver, and the ablation. So when you see here, the another major difference I didn't mention here, like ablation and irradiation. In ablation we use a focused lens, whereas in irradiation non-focused ray we used. So these are the wavelength. At a particular wavelength we have three different, UV, visible, and IR region wavelength laser we can use used for the ablation or irradiation based on our material target or decide property what we require. We can tune the material's property by means of tuning the laser property. So here when we use the particular lens, we can focus on the particular target of material. For example, I am taking a one target material. I need to dissolve this particular portion. If I keep ablating, the laser will point to one particular point. So when it hit the target, it generate the plasma flume with high temperature that can dissolve the metal into metal ions. So these metal ions react with the solvent and can produce the desired product. That mechanism you can see in the next slides. So these are the videos clips, like visibly you can see. Yeah. So these pulse laser technique called as a green chemistry process. So in our research, not only the application like water splitting is a green chemical process, but also synthetic process is also a green chemistry process, because we don't require surfactant or caping agent to control the size and shape. So for example, if you take a semiconductor material like a TiO2 or zinc oxide, which is keep on, even still the research is going on the TiO2. What they are trying to do at the recent research means, even nature also they are publishing a TiO2 research. They are tuning the property, or they are studying the mechanism. Some property they are changing. For example, in a chemical synthetic route, in order to tune the morphology or shape, size of the material, they are using a surfactant, or they are using a reducing agent. What will happen when you use? But in case of laser technique, we don't require any surfactant or a caping agent. What is the difference? Why we need to avoid? If I avoid, what is the advantage means? For example, all the electrocatalysis reactions are a surface reaction, surface between the electrode or electrocatalytic material and electrolyte. So it react. There should be a electrochemically active surface area, and there is a number of active sites. So this can be blocked by the surfactant or caping agent. When we use a chemical external reagent like surfactant, it is covered on the surface of material. It can block the number of active site, which can hinder the reactivity between the electrode and the electrolyte, that can be suffered either HER, OER, or whatever. So another thing is, we not required any reducing agent. For example, if I want to convert metal ions into metal nanoparticle or metal alloy, we required in chemical route means we required any sodium borohydride is a toxic reducing agent. But in case of laser technique, we don't need any such kind of external reducing agent. So how it can be reduced, that mechanism you can see. For example, one of the work I have shown here, which was published in chemical engineering in 2021. In this technique, what we did is we have integrated the sonochemical process and laser process. Of course, without sonochemistry is a one separate research topic, and laser is a different topic. We just merged these two techniques. What will happen? Let us say this nickel PD alloy we synthesized using a pulse laser technique. For synthesis this technique, in the initial step, we have ablated a nickel target in a methanol solvent. So once the target is ablated, we get a colloidal solution in a methanol solvent. So how this metal, when the laser hit the metal target, any target, it can dissolve, it can produce a metal ions. This has been reduced as a zero state. Nickel has a 3+ or 2+ state that can be converted into zero state. How it can be reduced? Because during for example, you can see, when I pass for here is like a cover image which we published. So this is a laser. This is one example, like I saw here, or here you can see. So the target is dipped in the methanol solvent. So in order to hit my laser on the target, it need to cross the solvent. So when the ions comes out from the target, it react with the solvent. So how this react means, during the laser process, the solvent get decomposed. For example, in case of water, it can decompose into hydrogen and hydroxyl radical. These hydrogen radical act as a reducing agent. So hydroxyl radical act as a oxidizing agent. It can leads to the formation of oxide material when I'm using in water. But in case of methanol, the OH radical is much, lesser when compared to the other hydrogen and methane radical. So these methane radical further decompose and produce the hydrogen radical. These act as a reducing agent, like metal ions to metal zero state. So this is how the we can avoid the reducing agent. So the similar process taken place in case of irradiation also, but we are not using a target material. Like we are not focusing a particular focus point, rather it is widely dispersed rays we can focus. So colloidal solution we can apply in case of irradiation. So in the next step, the nickel colloidal solution, we dissolve the PD salt, then we undergo a pulseless irradiation, and we can synthesize the nickel PD alloy. So the difference between the nanoparticle alloy and, of course, recently we work until high entropy alloys, high entropy oxides, high entropy phosphate. These high entropy materials also, the recent trend in catalysis, either of course they went to dimer, trimer. So single atom, initially they started with the single atom, double atom. Of course, they went on to high entropy single atom. Of course, in our research also, we have studied one recent, James, we reported high entropy single atom. But apart from this dimer, so between two atoms, there will be a bonding. Both are in atomic scale, atom, there will be a bonding. It will be interesting topic. So this is another recent topic which is going on. So of course this single atom side, that research, and there is another topic is called high entropy material. For example, here I have shown is a alloy. It may be a one material, bimetallic or trimetallic. When it goes up to 5 material, we call it as a high entropy alloys or high entropy oxide or phosphate, based on the cation and anion interaction. So whether this material formed as a whether 5 metal, if it is attached, whether can it as a high entropy, means no. We need to calculate the entropy changes. There is a one formula, delta S. If we calculate, if it is there will be high entropy, medium entropy, and low entropy. So these are the things. I don't want to deviate from the topic. Let us move here. So it forms alloys, means a single piece of material, like a cube. If it is forming a cubic shape, the paste, crystalline paste, should be a single paste. If it is a two mixed pieces, it is a bimetal. We cannot call it as a alloy. So if it is a composite, means there is a mixed paste of two material, we call it as a composite. We cannot call it as a one single material. So this is how we can able to produce, reduce the metal ions to metal nanoparticle. So what is the advantage of integrating the two technique? So as we mentioned, this laser also split the solvent and produce the radicals. Similarly, when we pass the sonication, this is the sound waves, which can also due to the cavitation bubbles, and it split the solvent and enhance the number of hydrogen radical. These, when there is a more number of hydrogen radical, it can be reduced very fastly. Yield wise is much better, but I am not showing much results. So and also when it is in under sonication, the shape and particles wise uniformly distributed. That is the difference you can observe here. So by having this kind of experience, we extended our research to the AUPT alloy for of course, this work was also studied for the water splitting. Here we studied the water splitting as well as overall hydrogen splitting. So as I mentioned, one full cell reaction means which contain one off cell, one oxidation and one reduction. In overall water splitting, it contains a hydrogen evolution reaction and oxygen evolution reaction. When I am replacing OER by the hydrogen oxidation reaction, what is the advantage? Why I want to replace this OER, means to reduce the energy. For example, in electrochemistry, there is a spontaneous and a non-spontaneous reaction. For example, fuel cells are non-spontaneous reaction, we not require any energy, rather it can produce the electricity. But here in this case of water splitting, it is a non-spontaneous reaction. So when we join oxidation reduction the circuit, we need to provide the energy. So how much energy is required? So for example, as I mentioned, the cell voltage is depends on the oxidation and reduction potential. But when we reduce this one, OER is a 1.23 volt, this one. So when I replace with minus 0.33, the overall cell potential is much more reduced. This was the evidence in using our experiment. So almost like 1.5 volt is we can save. So with less than minimum number of electricity, we can able to produce the high yield of hydrogen. So this is called a small molecule oxidation. So whether we are focusing only on a hydrogen oxidation, hydrogen molecule oxidation, no, we cannot. The researcher are focusing on the perfurol oxidation. What we happen, perfurol oxidation means perfurol it converted into puric acid. So perfurol is one of the derivatives, biomolecule derivative. It can convert it into value added product. So when there is a two optional reaction which can be separated by the membrane, one oxidation reaction, some molecules. In case of here, what is the product? Like hydrogen oxidation reaction, it can split N2 H4, it can produce either H2 or N2, nitrogen. So nitrogen is not much our interest, but in case of perfurol, it can produce a 2-puric acid. It is a organic molecule which can used for the various value added chemical, as chemical synthesis or some other uses. These can be monitored. So other reduction side, we can produce H2, and another side is two value added chemicals. At the simultaneously, we can reduce the amount of energy required to reaction occur. This is what the beauty of our work, like replacing a OER with the small molecule oxidation. So this is the concept of this work. Let us say this is the we studied the different ratios of AU PT, almost 5 combination we have studied, and we could see that highest PT ratio, it shows the highest HER activity. The highest HER activity is also shown hydrogen oxidation. This is the hydrogen oxidation LSV profile, linear sweep voltammetry. So the selectivity, if we take highest PT contained material is good for HER, good for hydrogen oxidation reaction. But whether it is same for OER means no. The result is not shown here. In case of OER, the PT 4:1. This material is highly active. Why? Why it is not? The same PT higher concentration is not active for OER means during the electrochemical reaction, OER reaction, the PT converted into PTO. So this PTO, surface oxidation state of this material hinder the OER reactions. So this is what we studied exactly in maybe in the next slide we we can show how we are studying the surface restructuring of the electrode material. That is what our real research. Of course, there are n number of people working on the water splitting, HER or OER, but why still we can able to publish means we need to study the reaction mechanism, how it is performing. That is the main focus of our recent research. So this is called a selectivity. So does the same material can be active for all the material, all the application? Oxidation reduction means no. So that we have to study. Okay. So you can, so far I was talking about the alloy, single atom or whatever, I gave some example, but you can ask this laser technique can be extended beyond metal nanoparticle or metal alloy, because I propose the mechanism for the reduction, how it can be reduced metal ion to metal zero state. You can curiously ask, can I extend this to the other non-oxide material or oxide material? Yes, we can do it. Here one of the example which I have shown here in last year we published in Carbon Energy, I think 19.5 impact factor in Wiley. What we did in this work is we taken a various, metal plates, cobalt, iron, titanium, molybdenum, we have converted into corresponding metal carbides. These technique, within 10 minutes, we can able to produce the pure phase of carbides in acetone solvent without any external carbon sources. Generally, in a typical metal carbide synthesis taken place a high temperature program reaction like a gas and solid phase reaction. For example, gas, we use methane gas. In furnace, they pass the gas, methane gas. When at high temperature, this methane decompose and produce the carbon fragments that can be, plus hydrogen. These metal precursor can be reduced using upon reaction with the hydrogen, and this carbon fragments is react with the metal source. It produce the metal carbide at high temperature reaction. But when we go for a high temperature reaction, it is not like a 5 minutes or 10 minutes reaction. It is a hour basis, like 3 hours, 4 hours carburization reactions. So here in this case, within 10 minutes, we can able to produce the pure phase of metal carbide without any external carbon sources. You can ask, so then how it can be produced? As I mentioned, solvent plays a major role. When I want a metal oxide, we need to use H2O as a solvent. It can split hydrogen and hydroxyl radical. So these hydroxyl radical act as a oxygen source, oxidation material. Of course, naturally it has the atmospheric oxygen also. It can convert into oxide. In case of, if I required, we changed a different carbon chained solvent. In acetone, of course, methanol, ethanol, it can form a gravity carbon on the layer also. There are n number of studies which we are, performing. But in this reaction, when we taken a acetone solvent, like we have taken a target metal plates, dipped in a acetone solvent, we pass the laser. These carbon decompose and produce a various carbon fragmentation. So this is the mechanism. When it laser heat at a particular place, it produces the plasma film at high temperature. It can produce the metal ions. So already in the path, laser path, there is a acetone. It decomposes. It produces a carbon fragmentation or carbon atom. These bind with the metal ions and produced as a metal carbides within a 10 minutes. That is the beauty of our synthetic route. Okay, we applied for the HER and OER. So there are various material I studied here, and only molybdenum carbide is the best for the HER. Why only the molybdenum carbide is the best for HER means? So that is the science beyond it. So it has a more D vacancies. So when there is a D bond vacancies much higher, it is easy to attach, bind with the hydrogen atom. So it can easily produce a, when there is a it plays depending on the solvent, electrolyte pH also. For example, when there is acidic medium, there H plus ions will be much higher. It leads to the highest HER activity. And in alkaline, it is favorable for the OER activity. But here in this case of molybdenum carbide, it attract hydrogen ion because of the highest D block vacancy. But in case of OER, cobalt carbide is highly active. So this is called a selectivity. So we need to select which material or which application is required and how it is performing. So what will happen? I have shown one of the example, in situ electrochemical Raman technique. So during electrochemically, like in situ technique Raman, we have Raman spectrum, we measured what happening during the OER reaction. I shown here only the OER, but we studied HER and hydrogen, various techniques also. We are studying in situ techniques, like how the reaction performing or what is happening during the electrochemical reaction. So these cobalt is easily attack. Affinity towards the oxygen is much higher when compared to the other material. So what will happen in alkaline medium? It easily attack oxygen. It form a oxyhydroxide as a active sites. So these active sites can I mean, this is the reactive species or active sites. These further we can validate using a DFT, theoretical studies also. So when there is a prolonged oxidation reaction, it again it converted into cobalt oxide. This is what observation from our studies. So we are taking a copper carbide. When there is a surface reaction, when we apply a potential, I mean energy, the surface can convert it into some reactive species by reacting with atmospheric electrolyte medium. So since it is a alkaline medium, it is attack OH ions and it form a oxyhydroxide. These act as a reactive site. This is what we observed using this study. Okay, I was given a brief introduction about entropy alloy. In this study, what we did is almost 6 material we taken. I mean, noble metal we have taken. Why we have taken this first study? I mean, not a first study. In these studies, when you start more entropy alloy, if you choose this noble metal, it is easy to reduce when compared to the transition metal. Noble metal, it won't easily oxidize, and also the reduction potential is much closer, all the noble metals, so easy to form a single phase. So what we did is we studied for the hydrogen production. For example, overall water splitting and overall hydrogen splitting. That what is the difference between overall hydrogen and overall water splitting, we have seen in the before slide, so I don't want to go in depth. So when I am replacing overall OER by the overall OER by the hydrogen oxidation reaction, almost 1.41 volt we can save, and we can produce the high yield. So this is the schematic scheme. So the beauty is, one is what is the if you take what is the wow point in this work, why this went to small, or why need to go for the publication, means one is the production of high entropy alloy in 5 minutes. That is the beauty. Without any reducing agent, within 5 minutes I can able to produce a single phase of high entropy material. So there is, as I mentioned, there is a calculation. We can low high entropy, medium entropy, low entropy. So there will be del S should be change in enthalpy. It should entropy. It should be a 1.5 above. That value is called as high entropy material. So when there is a high entropy, the property is much different. As I mentioned, there are chemical property will change it. I don't want to go in detail about it. So as we know, in overall water splitting, we have HER and overall OER. Here hydrogen oxidation and HER is taking place. So we need to study. You can ask, I have a 6 metal in this, 1 2 3 4 5 1, yeah, almost 5 metals with substrate, like another carbon, multi-wall carbon nanotube. Which is the active site? Whether all the metals is participating in a reaction, or only one metal is participating in my reaction, that we need to study. So which is the active species in a reaction, that we need to study a various in situ technique. I have shown here only the in situ Raman spectrum. For example, among this 5 metal, ruthenium and PTs play a major role in HER performance, and various, in case of hydrogen oxidation, PD is a highly active sites for the hydrogen. It plays a major role. It reacts with the electrolyte and it produces the highest nitrogen. Here in case of hydrogen it will produce. So what happened? For example, among the 5 metal, only 2 metal is participating. Remaining can be used for the enhance the conductivity. It is also play important. So it can
one-way interaction.
Sorry. Yeah. Maybe if I try to finish in shortly, sir. I can understand. Maybe we are running late. Okay. So we can. Yeah, sorry. Can you audible?
Yeah, please continue, sir. Yes, sir. You are audible, sir.
Yeah. Okay. Thank you. So here in the beauty of this work is to study the active species using a various in situ technique. I have shown here only the in situ Raman here. So the remaining it act as the synergetic effect, like whether it is a positive or negative synergetic effect. It based on you need to do the various experiment and we need to find out. So selection of these material also plays an important role forming a high entropy alloy. It should be a alloy, means it should be a single phase. In case if there are recently we started with the transition metal also. Various research is focusing, but I shown here only one research. So we can also do the transition metal. I mean non-noble metals also can be produced as a high entropy alloys. Not only high entropy alloy, we started with the sulfide, high entropy sulfide metal react with the sulfur metal, phosphide and carbide. We can extend this laser technique for the various materials, not restricted to only alloys or oxides. Okay, I think due to the short time, I want to wind up in within a time limit. So we have summarized the research published in 2024 from our group, and of course you can see our if you need to know more about our research publication, you can go through our website. So as I mentioned, we have a team which we are mainly focusing in the different field, electrocatalysis and photocatalysis. Some people are working on photocatalysis also. That means photoelectrochemical reactions and sensor and spectroscopy. Why I have categorized means like we mostly studied, as I mentioned, the levitated system in the first introduction slides, and like these spectroscopy studies, in situ spectroscopy studies, which we categorized in this. Some are like randomly I have splitted in a different category. So you can go through our research to know more about our recent works. So some of the pictures, like my boss and some of our research team and from the collaborator, they have visited India. So this is our home, and of course recently last year we visited Mahabalipuram and also Tanjai Periyakoil, and this is I mean Bangalore, and this is North India. So these are my children. And finally, I want to thank my boss, Professor Myung Choi, and some of like our team members, like research professor and postdoc and PhD student. Of course, you can see many Indian faces. For example, this guy is from Bangalore, and he is from like near Palani, Dindikal. He is from Dharmapuri, so yeah, Krishnagiri, Saranya, and he is from Tirunelveli. He is from Erode, and one more guy is from Chennai. So of course we are like open for the master and PhD student. You can apply, like we have a 2 semester intake. There will be like March and August. So in order to apply, I mean enter the March, we need to apply like a December, and for entering in August, we at least start from the June. The application process we need to start from the June. If you are, I mean your students or anybody is interested for doing a master or PhD, you can write to Professor Myung Choi or myself. And thank you for listening, and it's open for your question and discussion. Thank you.
Thank you, sir. Thanks for your talk.
Yeah,
So
thank
the
you.
session is open for discussion. So if you have any questions, you can type in the chat box, or you can unmute yourself. You can ask me. Participants, if you have any doubts, you can ask now.
Maybe you can also personally email if you want to make questions.
Excuse me, sir, this is Dr. Vijay Gupta.
Yes, please.
Yes, sir, I have one question, sir.
Yeah.
When we are doing the electrolysis, particular electrolysis, how to determine the potential, exact potential, what we are going to apply?
Okay. Can I answer?
Yes, sir, please.
Okay. So your question is how to select the potential. For example, I mentioned in the introduction this oxidation reaction. I think you can mute your this one. So as I mentioned, every electrochemical reaction it consists of two opposite reaction, either oxidation and reduction. So for example, in case of water splitting, it has a two opposite reaction. One oxidation is a OER and another one is HER. As I mentioned, all the oxidation reaction or reduction reaction, theoretical, it has a theoretical potential. In case of HER, it is a 0 volt, and OER, oxidation reaction, is a 1.23 is a theoretical standard potential. So standard potential means we need to provide a potential which is equivalent to 1.23. So can I give 1.23 to accelerate my reaction? Means mostly it is based on the catalyst and electrolyte medium. So definitely none of the material will be active at particular this much potential. So definitely it required higher energy. Higher energy means in case of potential. So power into I into V is a power, and the energy is in terms of power into time. That is, most of you are physics background that you know. So the electrochemistry is mathematically we terms as a in mathematically any graph, if you take all the known parameter we plotted in a x-axis, and unknown parameters which is provided in a instrument which gives in the y-axis. In electrochemistry, it is very simple. There is only two parameter. One is the potential and current. If you are giving a input as a potential, the output will be the current. When you are giving a current as a input, the output will be the potential. This is the electrochemistry. Very simple. All the experiment. So now let us come for the your question. How can I give the potential range? So first we need to know the theoretical potential. HER takes place at 0 volt, OER takes place at 1.23 volt, and ORR, reduction reaction, it takes place at 1.23. It is a reduction reaction. So that is what I mentioned, forwardic reaction and backwardic reactions. So if I want to perform this HER, we need to provide in a negative scale that you can randomly choose. For example, mostly what we do is 0 to minus 0.7, that in case of HER, because all the scale we need to measure in a RH scale. So we depend on the reference electrode which we are using. So if you are using a acidic medium, you can give the potential range 0. Roughly I'm saying minus 0.8. In case of alkaline medium, you have to give because there is a formula RH scale. It is very based on the pH. You have to reduce. You have to minimize. Then in case of alkaline medium, you have to scan minus 0 to minus 1.8. So we can convert it into RH scale. So why you have to scan beyond that? For example, 0 means it won't none of the material it won't react 0 potential. So we need to give extra, higher energy. So we have to provide a higher potential. You can ask why we want to provide a negative. Why can't we provide a positive? Because it is when the material which is close to 0 potential is we call it as a OER. Yes, if it is a positive negative, then it is a reduction takes place. H plus reduction reaction is called HER. If you scan like 0 to plus positive, because 1.23 only is OER takes place. In between, what reaction take place means there is a hydrogen H2 oxidation reaction will takes place. So we should not, in 0 potential, if it is a backward reaction, it is a reduction, H plus reduction. If it is a forward, reaction, H2 oxidation will takes place. So we should scan the HER reaction in the negative region. It can be selectively, we can choose randomly based on the material. For example, I have selected five material. Among this material, I mentioned the like AU1 and PT8 is the best HER activity because it is close to the theoretical potential. The theoretical potential of HER is 0 volt in RH scale. So like at 10 milliampere or whatever, if I measure all the potential, I mean current density, my potential is much lower. So the electrocatalyst can be
science, chemistry, science, botany, mind.
ಫಸ್ಟ್ ಸೈನ್ಸ್ ತೊಳೆದು ಆಮೇಲೆ ಕೆಮಿಸ್ಟ್ರಿ ತೊಳೆದು ಆಮೇಲೆ ಆಕ್ಸಿಜನ್ ಸೈನ್ಸ್
ಇವಾಗೆಲ್ಲ ಸರ್ ಅದು ಇನ್ವಾಲ್ವ್ ಆಗ್ಬೇಕು ಆಹ್ವಾನ ಮಾಡೋದು ಅಂತ.
Sir, B.N. Chandrasekhar, sir.
Oh, yes, sir.
Mute your mic, sir. Dr. B.N. Chandrasekhar.
Oh, yes, please.
ಇಲ್ಲಿ ಬನ್ನಿ ಸರ್ ನೀವು.
Sir, please mute your mic. Mute பண்ணுங்க அவரை. Yes. Yes, sir.
Yeah. Hope you understood my answers. Ajay Gupta.
I am still having the doubt because you are telling that it is close to the standard potential theoretical. My question is, suppose we don't know suppose we are having the new material, we don't know what is the theoretical standard potential. Theoretical means already determined. Suppose we don't know what is the potential, we want to know, we want to determine, then how to do?
Yes, that is what I mentioned. There is no, if you want to evaluate what is your potential of material, you have to randomly scan. For example, in case of HER, you have to scan in the negative range. It is fixed for all the material. For example, I have given standard like minus 0.8 potential, this window. When I scanned this window, I measured like at 10 milliampere, I used to get almost minus 0.04 volt or something. So there is we need to randomly scan in a wide range, then we can measure what is your material potential.
Suppose, sir, when we are immobilizing the material on the electrodes, there will be some resistance also, some human added some resistance. So it may vary also, na? Suppose if we will experiment on the different electrode, suppose the same gold electrode we are taking again and again, repeating, then the potential may change, na? Because every time resistance will change.
Yes. For example, I can understand. Your question is, for example, the reference electrode, based on the reference electrode and electrolyte pH, it vary. That is what I mentioned. When you take acidic medium, you need to choose AgCl reference electrode. When you are using alkaline medium, you need to use Hg and HgO, mercury and mercurous oxide. So because if you use in acidic condition, if you use AgCl, it can oxidize. AgO it will produce, and it will it will change the entire electrochemical reactions. So the selection of reference electrode must be, you should know, mainly AgCl and HgO. HgO in case of alkaline medium. Alkaline means KOH solution or NaOH solution they will use. Let us come to your question.
No, actually, suppose we are doing multiple scan. We are doing water electrolysis, and in water electrolysis we are doing multiple scan. When we are doing the multiple scan, then definitely some of the impurities will be deposited on the electrode surface. And when the impurities are getting deposited on the electrode surface, then in the next scan that value will not come.
Maybe your concern is maybe if you do single cell and H cell, there is a membranes. If you use, if I am rightly understand, you are performing oxidation reduction. If you use single cell, definitely this oxidized product will be interfere in your reduction case. For example, as I mentioned, one example, peripheral oxidation. The peripheral oxidation, it gives the puric acid product in the oxidation state. If you use a single cell, this puric acid product, it will go to the reduction part, and it can convert. It goes to the undergo the reduction reaction. The product will be different. But when you are using the gas-based reaction, mostly like hydrogen oxidation or OER, we expect this gas will be evolved out, so it won't interfere much. So people mostly they are using in a single cell, like there is no membranes. Without membranes, they perform in a single cell. The O2 gas, they are expecting that all will come out. Of course, O2 dissolve in your water or alkaline, whatever medium, in liquid medium. These also undergo for the reduction reaction. That is what you are concerned, right? So in this case, when exactly you have to use membranes, so you need to separate oxidation reaction and reduction reaction. When we are performing, you should know that the electron flow takes place from the oxidation to reduction, and during if you use proton exchange membranes, only H plus will transfer from the alkaline anodic side to cathodic side, proton membranes. If you use anion membranes, the anions will be transferred from the cathode to anolite. So when you use the membrane, suitable membranes, then the oxidation product, it won't interfere to the reduction reactions. Only you will get only HER and only OER. So this you can get clear.
Okay, sir. Okay, sir. Thank you.
Yes, sir. Thank you, sir. We can call the next speaker, sir. Thanks for your presentation, sir.
Okay.
We are also
okay.
Janita, just a minute.
You have electrified our minds with your insights on the topic pulsed laser technologies in electrocatalysis, sir. Thank you for sparking new ideas, sir. You have not only shared your expertise but also a part of yourself with us, sir. We are grateful for the time you shared with us, sir. Thank you.
Yeah, thank you, ma'am. So shall I leave now?
Sir, yes, sir. Please check with JS, sir.
Yeah. I think he is there in online. Otherwise, I will let him.
Okay, sir. Thank you, sir.
Thank you.
Another spark of creativity is about to ignite as we move forward to the second session of this event. We are honored to invite Dr. Jayesh Cheriseri, Brain Pool Fellow and Research Professor in the Department of Chemistry, Gyeongsang National University, Republic of Korea. His current...
Just hold panama.
Okay, sir.
Yes. Participants, please wait for 2 minutes. The guest will join within 2 minutes.
Hello.
Yes, sir. Sir, welcome, sir.
Yes. Yes. Okay.
Archana,
Thank you.
start
I will share my.
Sir, just a minute, sir.
Yeah.
Just a minute, sir.
Okay.
Archana, now we can start.
Another spark of creativity is about to ignite as we move forward to the second session of this event. We are honored to invite Dr. Jayesh Cheriseri, Brain Pool Fellow and Research Professor in the Department of Chemistry, Gyeongsang National University, Republic of Korea. His current research focuses on the synthesis and electrochemical applications of new generation ultra-thin layered 2D materials. He is holding a position among the top 2% of the scientists globally as recognized by Stanford Elsevier rankings. He is ensuring the integrity of scientific research as a reviewer for esteemed journals like Nature Communications, Sustainable and Renewable Energy, and many more. Dr. Cheriseri is a member of the Royal Society of Chemistry and has a H index of 27. He also published 65 scientific articles in peer-reviewed international journals and contributed to 25 book chapters. He has delivered several keynote lectures at various international conferences and academic institutions. We are honored to have you share your knowledge with us, sir. Sir, please.
Okay. Thank you for that nice introduction. Can you see my slides?
Yes, sir.
Okay. Thank you for the nice introduction. And I myself, Dr. Jayesh Cherusheri, I'm a NR of Brain Pool Fellow, and I'm from the same like previous speaker, Dr. Giri. So we are working on the same department, Department of Chemistry, Core Facility Center for Photochemistry and Nanomaterials. And I'm very happy and to be a part of the third International Faculty Development Program on Advanced Functional Materials, Energy, Environment, and Sustainable Development. And the title of my talk is Two-Dimensional Layered Materials for Futuristic Supercapacities. So before starting my slides, I would like to uh, make a notice that I'm a Brainful Fellow. So this Brainful Fellowship is a postdoctoral fellowship for the invited scientists from all over the world. So every year there are 2 sessions. So they will call upon for these new projects by the Korea, and the fellowship will be for a minimum duration of 3 years. So those who are participants and those who are their friends or whoever it is, they have good profile, research profile and skill sets, and also ambition to do research. They can apply for this fellowship in South Korea. And the first call, there are 2 calls in a year. The first call has been released, and the last date is 1st April 2025. So those who are interested to be a host, like if you want a host that is a professor from the reputed university, we are always welcome to contact with us. So we will process your applications, and you can contact either professor or you can be in touch with me in my email ID, jspuli@gmail.com, and the or with my LinkedIn ID, Dr. Jayesh Cherushiri. So the importance or the attractiveness of the Brain Pool Fellowship is the salary. So as we know that this is in the Asia, this is the highest paid fellowship for the postdoctoral. So this is minimum salary is 5 million Korean won to, and it can vary to 25 million Korean won. So 5 million Korean won, it comes around more than 3 lakhs Indian rupee. So this is one of the best chance for all the faculty members or the renowned scientists who are working abroad, like all over the world, so they can apply for the fellowship. And we are very happy to host fellows from maybe the faculty members, those who can take leave for 2 years or 3 years, so they can accordingly plan their leave, and they can apply for this Brain Pool Fellowship scheme. We have wonderful laboratory in our university, and our university is the well ranked university in the world, and also this is one of the flagship university in Korea. Okay, so like Giri explained, so we are from the Gangsang National University, and we have 4 campuses, and we are from Gajwa campus. It's from the Jinju city, and it's a very beautiful city with a very good landscape. So you can see that this is our campus. This is the entrance, and we have a straight road towards our building, and this we located at the building number 28. We have the core facility center, and this is the laser photochemistry laboratory, and this is our director of the core facility center, as well as the head chemistry department, and also our mentor and our professor in our group leader. Okay, and same like we are the team leaders. And we have many PhD students. Many of them are from Korea, but although numbers are less, but some of the students, like 5 to 6 members, are PhD students are from India. And also we are encouraged to welcome these new PhD students from India to do their PhD in with us in our laboratory, and they can avail the facilities of the Korean Research Fellowship schemes. There are many various fellowship schemes are available. So these are the options available for the PhD students. So you can go to this website, mychoicelab.gnu.ac.korea for more information, and you can contact either professor or me or Dr. Giri. So we will process your applications. We will guide you for the best of our knowledge and belief, and we will help in processing your applications. Okay, so come to the talk. Outline of my talk is like discuss about supercapacitor technology, and uh, some glimpse about supercapacitors and various electrode materials for supercapacitors, and in the two-dimensional layered materials which are used in the supercapacitors, and will little bit emphasize on the MXins and also the futuristic applications of electric vehicles or electronic wearable applications of these supercapacitors. So starting from the supercapacitor technology terminologies, we have two types of supercapacitors. So the supercapacitors are electrochemical powering devices. So as we know that these supercapacitors can deliver high power, but will have lower energy. So as shown in the Ragon plot, so where fuel cells can have a high specific energy, whereas the supercapacitors will have high specific power. So there are two types of supercapacitors, basically electric double layer capacitors and pseudo capacitors, which are exist in the market, where electric double layer capacitors are very good for uh, delivering high power, whereas pseudo capacitors are very good for delivering high energy. So this is the basic mechanism. We can see this. You can see here we have three different models, which explains the electrochemical double layer formation and the charge storage of in electric double layer capacitors. So we need large surface area electrode active materials for the charge storage. So based on that, so based on the formation of the electrochemical double layer at the electrode electrolyte interface, we can achieve the charge storage. So we need an electrode material with large surface area and a good electronic conductivity, that is for the transfer of electrons to the current collector, and we need to get it to the outside the output circuit. And second category is pseudocapacitor. So there are two types. One is the surface redox phenomena. Another one is the intercalation pseudocapacitance. So the first one is surface redox, is the redox active material will be participating in the reduction oxidation mechanism, and it gives the charge storage. Second is in the case of lithium ion metal ion capacitors, like lithium ion capacitors or potassium ion capacitors, we have intercalation phenomena, where the ions will intercalate through the layered materials, and that gives rise to the storage of charges. So these are the two main categories of supercapacitors. And also I would like to point that supercapacitors are otherwise called electrochemical capacitors or ultra capacitors. So these all terminologies they use interchangeably, but all are the same. So as per the Web of Science data on the supercapacitor, you can see that this is the research in the supercapacitor is it's almost saturated. So if you see the different disciplinaries, material science and engineering, the multidisciplinary, we have almost 22,000 articles published so far, and a total of 55,469 publications to date. So, among which there are articles, review articles, and proceedings. So you can see that this value after 2022, you can see that this is almost getting flat band. So this is almost the traditional supercapacitors are in a place of saturation, or you can say super saturation, because it is very difficult to publish a paper in this supercapacitor field due to this many number of articles. But still, people worry about why we need to do the supercapacitor, but it is very important that you will come to know in the coming slides. And there are a lot of rooms available for doing research. The mechanistic studies are lacking in this supercapacitor, because since the design of the supercapacitor is very easy, so people just go for the simple device, simple electrode material development, simple characterizations, and also the device fabrication, and report their manuscripts. So this is what the reason this now total number of publications became above 55,000. But still, the mechanism studies are still lacking in the literature, which is very much important for making it for the commercial supercapacitor. Now, just I would like to start with the news, but although not good, But in recently, like in last November 12th, we had a news that in Canada, Toronto, there are 4 Indians burned to death in a car after Tesla electronic doors failed. Reason and this this is the car, the Tesla Model Y. So this car became a not met an accident. It became the uh, battery problem. Okay, so as we know that all the electric cars these are very heavy, costly. Model Y, I think it around 60 to different variants, around 60 to 90,000 US dollars cost, the cost to buy. Okay, so this one it got this condition. It's just because of overheating of the one battery. So once they troubleshoot the postpartum examination, so they found that this overheating, this is called a thermal runaway problem. So if you can see that this is what is thermal runaway problem. That is nothing but the overheating in one battery cell triggers the chain reaction. So there are number of cells. There are thousands of battery cells in a Tesla unit or in any electric car unit. So if one cell is damaged or if one cell having some problem in the functioning, it can overheat and it can make fire. Now what happens? We have all the advanced electric cars. I think now in India, when compared with other cars now, Kia Motors, that is in our South Korea's very brand car, Kia. So they are having high ambition for the Indian community. So what is the reason why it is getting attracted to the people is because of its easiness in operation, because everything is operated with the help of sensors. So there are more than 100 sensors in the operation of the car. But now, what is the demerit of the car? This is the demerit, which I said. When when there is a fire, what happens is that this sensor system will get burned. Once your sensor system get burned, you cannot come out from the car. So that is the one of the main difficulty in the electric car. So there are some, because you know that every sensor it needs energy. So if needs energy, if it get energy, then only it will start releasing the car doors, even if it is an accident. But if the sensor system got burned, how it will open? So that was happened for this fiery accident happened in Canada just 6 months ago. And so why I pointed out this example, this shows the importance of supercapacitors. So supercapacitors are not just a device, but this is the future for all the electric vehicles as well as hybrid electric vehicles. We talk about different energy conversion technologies. For example, like there are various technologies. So we have conversion technologies like solar cells, wind turbines, even the liquid mediated like photocatalysis, electrocatalysis. There are various techniques, we say energy conversion technologies, but all these technologies they convert it into electricity. But while storing charge, we need lithium based batteries. But what is the problem? Lithium batteries cannot give power. It can give only energy. So what is energy and power? Energy means how long you run, that is energy, and how fast you run, that is the power. So these are the two, we can say, specific energy and specific power with respect to the device. So in all the applications, in the futuristic applications, supercapacitors are an important or a mandatory component. So that is what I'm starting with this news. And as you see, this electric vehicles battery or supercapacitor pack, of course, in India also we started making the plans for the electric vehicles batteries or supercap packs. But so this is actual this vehicle, the electric vehicle. Now only that this chassis will be enclosed. So this is the pack below which you have motors and also the battery packs, and also in this battery pack there will be supercapacitors. So supercapacitors are very important component of the any electric vehicles battery pack. So this battery pack also contains supercapacitors. Why we need supercapacitors? As I mentioned before, supercapacitors need to give high power. So you need acceleration. So Tesla car, it can reach 100 miles within 5 to 6 seconds. So you can imagine the amount of power it can give, the supercapacitor. So there are supercapacitors and batteries. So batteries, nothing but lithium ion batteries. So as you know that lithium batteries, about lithium, so which uses lithium, so it is highly flammable. Okay, so now we have a futuristic devices which is called a supercapacities has been developed. So that is our I pointed before that we will talk about some supercapacities. So these supercapacities are previously known as battery type hybrid supercapacitors. So there was a new name has not been given in the previous literature. So you can see they interchangeably use battery type hybrid supercapacitor or battery type supercapacitor or battery type capacitor. There are different terminologies they use. So the only thing is that one of the electrode which you use is a battery grade electrode, and you use aqueous electrolyte, not organic electrolyte. So as in the case of lithium batteries, we use lithium as well as organic electrolytes. So these both are not only harmful to the environment, but also it is they're flammable. So if any small problem happens in this in single cell, that single cell, and also you know that this how we are getting the output voltage, very high voltage. Even the small toy cars for our kids use, so that one is 22-volt DC. How we are getting that output? It is not one battery cannot give that much voltage. So we assemble the cells in series and parallel combinations, the basic physics. So then we get the required output, how much voltage we need, how much energy we need exactly. So such cells they make in series and parallel combinations to make the battery pack. So there will be lithium batteries, there will be supercapacitors. So in a supercapacitor, so already I mentioned that lithium ion batteries will have high energy density, but they don't have power. So that lacks power. So supercapacitors are they have high power density but low energy density. So this makes in the development of novel device like battery type hybrid supercapacitor or supercapacities. So this terminology is given by the supercap from supercapacitor and ATTERE from battery. So these together it comes to be supercapacitor. So the supercapacitor advantages are the same, like they use aqueous electrolytes, even if there is an accident or there is no thermal runaway problem because these are water-based electrolytes. And also we don't use lithium in the electrodes. So these are very safe devices for the futuristic electric vehicles. Not only for the electric vehicles, we have various type of electronic wearables like gadgetries, or we have many different types of electronic devices. So these supercapacitors can be a safe power source for those devices. So that is the importance of supercapacitors. Come to the electrode materials. So we have a variety of electrode materials which are developed. One is the traditional materials from the past. We are using activated carbons, carbon nanotubes, graphene, and also conducting polymers, polypyrrole, polyaniline, etc. And we had transition metal oxides like manganese dioxide, vanadium pentoxide, etc. And there are not only that traditional materials. Nowadays, we have many different materials for the application of electrode as an electrode in the supercapacitors. So one of it is the black phosphorus. Other is polyoxometallites and also metal organic frameworks. And we have amexines and we have nitrites and nitrites. Yeah. So these are the different electrode materials. So among these different electrode active materials, these layered 2D materials become very important in the case of supercapacitors. As I mentioned, supercapacitors, they have a mechanism which is uh, it is like battery type. That is, it will be what the electrode mechanism will be based on the diffusion controlled mechanism. So for the diffusion controlled mechanism, it is always recommended layered 2D materials. So that is the reason layered 2D materials became very important in the case of supercapacitor electrode fabrication. So these are the different 2D materials which are available. Graphene is the fantastic material or the evergreen material which is developed long back. But again, you know that this the synthesis and the cost is a bit issue. That is the reason it is the commercialization of this material is become still it is a issue. So the devices based on graphene become very costly. Okay. Second 2D material is the transition metal dichalcogenides. For example, we have the metal chalcogenides like cobalt sulfide, nickel selenide, nickel like etc. or telluride based material. So basically, these transition metal dichalcogenides also we can make layered 2D materials. So not always these TMDs form layered 2D materials, but we can optimize or we can tune the precursor concentrations in the nature of the precursors as well as the experimental conditions to make these TMDs layered 2D material. Another fantastic material is HBN, hexagonal boron nitride. So we have a layered structure. So and also another vastly studied material is MXenes, and it is one of the widely explored new generation material, MXenes, and also black phosphorus is a relatively new member in the family, not explored much. And also there are some other categories also. So other categories are nothing but metallines. So you can see these metallines are nothing but the 2D layers of highly electronically conducting materials like silicene, germanium, etc. So the metallines are highly important for a various of applications, not only in the energy storage applications. There are ORR applications, here to ORR, HER. So there are a variety of applications they are using. But this field is very new. So those who want to work on new materials, so metallines will be a great choice for them. And one of the another second latest material or the least explored material is M-beam. So if you see these metallines and M-beams, you can see very less number of papers in the literature, which shows its potential in the futuristic research. So those who want to look for a new material, or I want to do a research in a new field or with a new material. So always these metallines and M-beams always will be a choice. So there are different M-beams, so ruthenium boride and chromium boride, zirconium boride. So there are various type of M-beams are available, and you can select and you can do for the research. So what are the requirements for a good electrode active material for supercapacitor? So in the case of layered 2D materials for supercapacitors, we have this we need a mesoporous electrode structure. So this is for the easy movement of the electrolyte ions through it. So most of the ions reside in the mesopore range. So we need the easy flow of electrolyte ions through the pores of the electrode architecture. So we need a mesoporous layer. So it is easy to get a mesoporous structure when we use a layered 2D nanosheet. So one is the design of the mesoporous layer in a layered 2D nanosheet. It is one of the very important criteria to achieve high performance when we use it in supercapacitors. So not only that, we can make maybe the whole structure, it can be mesoporous, or it can be the base layer, it can exfoliate, and it can make individual layer, it can be mesoporous. So there are two different ways. And also, not only mesoporous, what is the pore size? What is the pore shape? What is the pore size distribution? These are also important in the case of an electrode. It's not only mesoporous. So what is the type of pores, what is the shape. So you can see that this is circular, this is cylindrical, and also so it can we can design in a with a combination of this or individual in order to achieve high performance. And also we can make a multi mesoporous layered on the nanosheets. So that is one of the latest research is in this field, where we can make the maximizing the electrode surface area by keeping the mesoporous layered structure on the both sides of the uh, layers. So one is the latest research is Janus nanosheets. So you might be knowing these nanosheets are one sided. This is a single sided mesoporous layers. And what is the importance? Importance is that you can easily the transferability of the membranes or the electrode membranes are the fantastic property of these Janus nanosheets, where you can deposit and you can easily transfer into an electrode or any other surface with then you can utilize it as an electrode active material. So these whatever we are I'm discussing is not only for supercapacitors or supercapacities. These are also applicable for batteries and other type of electrode applications, because most of the electrochemistry aspects this all works, because whenever this electrode is in an active medium like electrolyte, so this all these electrode architectural designs will help in achieving the high performance in any device. So come to the MXins, the highly explored, and you can see that in every journal, in every issue, there will be 1 to 2 papers will be based on the MXins. So that application can be anything, but it is an n number of publications in a year for the MXins, because we have number of choices. So MXins, so it is not a metal carbides. So we can have metal carbides, we can have metal nitrides, or we can have metal carbonitrides. So there is a combination of car, combination of carbon or nitrogen. So still there are many type of MXins are not explored yet. Many are in they published as the theoretical calculations and only predictions, not yet used, because there is a lack of research in this 2D material MXin for the not only for the electrochemical energy storage in as a whole. Very less is explored in the MXin. So there are a lot of room for doing research. So starting from the Yuri Gagauz's group in 2011, they discovered this titanium carbide MXin with hydrofluoric acid etching method. And further, there is a fast development in this field of developing MXins with a bifluoride etching method, and also some amine assisted delamination in 2015. And also we had a lithium fluoride HCl etching method, which is one of the widely used method nowadays, and also the mild etching methods without using lithium fluoride. So there are various methods available to synthesize 2D layered MXins, which are highly fascinating materials with very good conductivity. So you can use it for various applications. So MXins are derived from max phase. They are respective. They called max phase. So M can be a metal, and A will be the interlayer. Mostly they use it as aluminium, and X can be any other, like it can be carbon, nitrogen, or it can be carbon nitride also. So based on that, there are different type of MXins. So we remove this. We can remove this A atoms from the max phase. So A will be removed, so remaining will be M and X. So we call MX and INS. INS nothing but ENE. We terminate, it represents 2D layered material. So whatever you call it as ENEs, you need to understand this is the 2D layered material. So MXenes, MBenes, silicines, germanine, phosphorine, borofine, all ENEs. ENEs are 2D layered material. It is not like a graphite like structure, but it is a graphene like structure. So that it is to be to distinguish That graphene from graphite, we call graphene as graphene. Graphene are single layer graphene, maybe a monolayer or single layer graphene or double layer graphene. So similarly, we have MXenes are nothing but these are one or two layers or some layers of 2D layered materials. So they are called MXenes. Now, the synthesis and the challenges of MXenes. So main synthesis of challenges you can say in the pre-synthesis, one of it is high toxicity because we are using mostly we use lithium fluoride and hydrogen fluoride or LIF or HCl based mixture to remove the aluminum layer, and also a good max phase. A good max phase is very important in the research. Many people they buy max phase from different companies, but they try to reproduce the research from their respective report, but they won't get it. And also we also faced the same difficulty initially. Why this? Why we are not able to synthesize MXin from the max phase? Because the which company you are buying the max phase is very important. You may get a cheap price, but don't go for it. It will you will not get it will not get exfoliated because it will not be having a laminar structure. So that is very important. And the second challenge includes in the synthesis. What is the problem? Because conventional hydrothermal method we use uh, for the exfoliation. So it takes almost 48 hours. Sometimes it may take more than 48 hours. It may not exfoliate. So high temperature is required, high chemical consumption is required, and also we get a low yield. Once we centrifuge it and we dry, we get very less material. So compared to conventional hydrothermal, there is a new method which is called microwave hydrothermal. Usually I worked mostly. So this we have short duration. We have a processing time of just 20 minutes time, and also it requires low temperature, and it requires low chemicals, and also high yield of production of MXin. So these are the challenges related to synthesis. And once we synthesize MXin, there are again challenges. One is the that is called post synthesis challenges classified as. One is the surface terminal groups. So this problem is not only for MXene, there are various 2D layered materials also. This problem still exists because you need to imagine these are layered, these are atomic thick layers. So how many? Maybe 3 layers or 4 layers. So they are highly active. So whatever it is in the terminal groups available, they will just make bond with the terminals. So there will be unsatisfied bonds in the structure in the surface on the surface. So definitely, so always you will have terminal groups attached with these 2D layered materials. So that is one of the major disadvantage of course we can say that for the 2D layered materials, but that we can tune with surface modifications or functionalization steps. So the surface terminal groups are one of them, and second thing is problem with this storage of the MXene, that is the oxidation. So although we prepared titanium, for example, we prepared a titanium aluminum carbide, we took as max phase, then we synthesized the titanium carbide MXene. Now I want to store this material. If you even if you dry the material, it will get oxidized. So the material, you can see that out of the black material you can see the white spots. Maybe those who work in the field, you may notice that, or maybe there will be a change from the color of the MXene you prepare. So the white is nothing but titanium dioxide, so it converts into oxides. So that is one of the major challenge in the oxidator. So you can use, instead of normal drying, you can use freeze drying, and also you can use in an inert atmosphere to store. So it is very delicate in storing the MXenes also. See, these are the challenges related to the 2D layered material MXene. So I would like to explain a little bit about microwave hydrothermal synthesis. So as I said, if you use microwave assisted hydrothermal method, it is a fascinating method in the synthesis of a variety of materials, not only in the MXenes or layered materials. All materials we can use this microwave as the power. So instead of joule heating, we have microwave is giving the power. So, but the machineries are a bit costly, but still, when compared with the time of experimental process or the reaction kinetic, this method is having lot of advantages. So in on our research, we take this titanium aluminum carbide, and we use the microwave hydrothermal reactor. In the reactor, we keep this titanium aluminum carbide, and then we exfoliate it using that chemicals, HHNs. Then we get titanium carbide MXene. So when we write any MXene, some of uh, the general way of writing or the correct way of writing is Ti3C2TX. In many people, in many papers, they don't report this the last terminal groups, which is not correct. So it is always better to add the TX. TX is nothing but terminal groups. But in our simplicity, we some of the papers we may not uh, show that TX. TX are nothing but terminal groups. So, and then once we exfoliated it, once we do the microwave, and then we get the delaminated titanium carbide MXenes. So these are the steps, different steps involved. So we use we first is, as I told before, we need to buy the good MaxiPhase from a good company with a good price. So that is a bit, it will be a bit costly for doing research in MXin. So, but still, if you want to get a good product, you must use a good MaxiPhase. Otherwise, it is a simply wastage of time. So first we dissolve that max phase in the LiF HCl mixture. Then we stir and then send it to the autoclave. Then we use the microwave hydrothermal reactor. So there will be production of in situ HF and intercalation and formation, and then removal of aluminum chloride from the structure. So this is how we remove aluminum from the titanium aluminum carbide max phase. So once we wash it, we need to do multiple times of washing, and the pH should be more than 5, and we finally we get a delamination of MXene. Now we got MXene. It is always important. What we do usually what we do is we discard the supernatant part and we take the bottom of the material. But if you want very thin layers of MXene, for example, 2 layer or maybe less than 5 layers, you cannot. It is very difficult you to get that kind of MXene from the sediment. You want to take the supernatant solution, then you freeze dry it, then you will get the real MXene that is less than 5 layers. So that is one of the technique. And then once you freeze dry it, you can remove it and you can store it immediately in a container without undergo air oxidation. So these are the different steps which I showed. So we add the H and mixture, lithium fluoride and HCl, and then we add the max phase powder. Then we sonicate it for 30 minutes. We give for the high pressure Teflon reactor, and then we put it in the microwave. So we use the FlexiWave microwave reactor. So once we have that, once we take out, then we wash it. Then again the supernatant we remove it. Then again we sonicate it. Then again we remove the supernatant. So whenever you remove, if you use these multiple procedures, so what happens is that those are undetached single layer or 5 layer, less than 5 layer MXenes will be detached, and you will get a more and more single layer MXenes. So once you freeze dry, you will get the MXene powder that is from the sediment. So you need more yield. You need to, of course, you need to take the bottom part. But if you need a very less yield with a small number of layers, then you need to go for the supernatant. So that is the technique. So as I discussed before, these are the head of stem mapping for the titanium carbide MXene. So you can see that instead of titanium and carbon, here you have fluorine, chlorine, and oxygen. So these type of terminal groups, fluorine and chlorine, which are coming from the hydrogen fluoride and lithium HCl and lithium fluoride. So the HNs. So uh, remove these terminal groups. So these are chlorine and fluorine. They hinders the electrochemical performance when we use it in a battery or supercapacitor or supercapacitor. So this is very important. So not only uh, synthesizing the MXene, but the purity of the material. What is the terminal group? Maximum terminal, the terminal group in the MXene also very important. So you can do an XPS analysis for the titanium MXene, and you can know that what is the amount of terminal groups present in the uh, MXene. So you can see that these designated regions, you can see that this is oxygen. So you can have a very elevated percentage of oxygen in the spectra. So the bottom spectra, the black one, it shows the titanium aluminum carbide, and the top one is the XPS spectra of the titanium MXene. So you can see that this oxygen is got reduced, but not zero. And also fluorine. Initially there was no fluorine, but once we synthesize carbide material, like after the MXene synthesis, you got fluorine in the structure, and also as a terminal group. And also this also important, aluminum. So aluminum, we say selective removal of aluminum from the MXene, but in reality, all the aluminum will not be get removed from the from the max phase. So there will be always some amount of aluminum present, but our target should be, it should be minimized. So there should not be major aluminum. So that means that max phase is not changed into a maxing. So that is so this XPS analysis is a very good surface analysis technique to get to know that not only the composition, the structure, and also the terminal groups. So previously I discussed about we synthesized the titanium carbide MXene. Also, so previously I explained that you can see this. We used we purchased max phase titanium aluminum carbide, and then we exfoliated it with the help of microwave hydrothermal synthesis. So similar thing we can do also. We can prepare, we can synthesize if we feel that okay, we don't have money to buy the max phase, but we have the facilities, we have a high temperature furnace in our laboratory, then yes, why don't we synthesize the max phase ourselves? So this is one of the work we have done. This we had aluminum carbide. So this is one of the collaborative work we did long back. So they have used aluminum nitride and vanadium powder, then went for the ball milling, and then cold press it, then heated at a very high temperature, 11 degrees centigrade, and then we got vanadium aluminum nitride. So that's what the title we made, M2 Max 2 MXene. So we can use different precursors in order to make max phase. Once we make max phase, we can exfoliate ourselves to MXene. So here they have used this DMSO sonication, centrifugation followed by DMSO sonication. So it is a very simple technique to produce vanadium nitride based MXenes. So these are the two techniques which I explained. One is max phase to MXene, and one is you can make max phase, and from max phase again you exfoliate it to MXene. So these are the two techniques we can go in the case of MXene. So now I will give some examples of for what you say, the supercapacitor performance of the 2D layered materials. So maybe I say 6 to 7 different types of 2D layered materials. So first I will go with transition metal dichalcogenides. That is one family is the big family. So nickel sulfide is one of the member in that family. So first I will explain the 2D layered nickel sulfide material for the supercapacitor. So as I explained before, the microwave hydrothermal method. So we synthesized this nickel sulfide nanosheets and then use it for the supercapacitor applications. So you may be doubt that why it is, what is the difference, how we say that it is a supercapacitor or a supercapacitor. What is the, how we give the names, why the nomenclature as a supercapacitor or supercapacitor. It's very simple. If you see the, you see the CV curves. So in the CV curves, we will do a calculation. By using CV curves, we have a Dunn's method that is called a Dunn's kinetic method. So we will find out the B value. So there is a, there are particular equations. So we have, we can calculate the peak current and the effect of scan rate. So we can get some a value called B value. So based on that B value, we explain that whether it is a supercapacitor or it is a supercapacitor. So more details you can go to this journal. This is one of our recently published paper. So you can get more details. So from CVCur, we do the calculation, and also you can get information from the GCD curves, the galvanostatic charge discharge curves, like these curves. You can see that there are, the discharge is, will have different regions. So this, you have a fast discharge, then you have a plateau, and again you have a slow discharge. So this type of curves are, it depicts battery type characteristics. That is the reason these electrode materials are called supercapacities. So in a supercapacitor, we don't call it as a positive electrode and a negative electrode. We call positive electrode as a positrode and also negative electrode as negatrode. So in a supercapacitor, this is just to distinguish it from the supercapacitor. So this is the nomenclature we use it in the literature. So we have positrode and a negatrode. So positrode usually will be the 2D layered material, as I'm going to explain in these next coming slides. So this is the nickel sulfide was the positrode, and the negative electrode will be the activated carbon, commercially available activated carbon, which is a capacitive electrode. So that is the reason, one we have negatrode, we have a capacitive electrode, positrode we have a battery type electrode. Hence we call it as the device as a supercapacitor. So the next one is, I think we have 10 minutes left, right?
Yes, sir.
Okay, I will just move a bit fast. So we have this titanium carbide. Next is the second category is the MXene based supercapacitor. So we can have the synthesis method as simple as we can take a carbon cloth and we deposit this MXene or any other battery type of electroactive material on the carbon cloth, and we dry it, we get the electrode. So these are the different morphologies which we obtain, and also the elements distributed over the coated surface. So these are these kind of electrode modification we can make in a very simple modifications, so that we can make supercapacitor electrodes for supercapacitors. So the third category is the molybdenum aluminum boride. So these are the MBean. So this is one of the molybdenum aluminum boride we have. Now you go for the etching method and you can get a molybdenum aluminum boride. So where you need to be very clear that in the case of MXene, we don't write the aluminum there. But in the case of MBeans, we need to write aluminum, because it is not easy to remove complete of aluminum from the materials. So sometimes we always get some of the layers with the parent material, the interlayer materials. So we can go for the micro supercapacitors with these materials, because we don't want a bulk electrode materials for functioning of the micro supercapacitors, and we can get a very high power density and energy density. So you can see that in the dragon plot, this particular MBIN have almost 100 watt hour power, watt hour energy, and also adequate power density. So the fourth 2D material is phosphorine. So phosphorine is also one of the new coming or new generation 2D material. So synthesis is very easy. You can use red phosphorus. From red phosphorus, you can add the ethylene diamine. Then you mix it and then add the NaOH solution. Ultrasonication, you will get a black phosphorus. So this black phosphorus, it is also important. Some people think that phosphorine is same like black phosphorus. No, black phosphorus is same like our graphite. From graphite, we can synthesize graphene. It is something like that. So black phosphorus is layered material, but not a single layer or less than 5 layers. So once you exfoliate this black phosphorus, you will get a phosphorine. These are single layer or 2 layers. So again, you can use it for the application. And the fifth category is borofine. This is one of the new generation material, but synthesis is you need a chemical vapor deposition technique. So you need sophisticated machineries to make a single layer or maybe less than 5 layers of borofine. But this is one of the growing field in the area of electrochemical devices in supercapacities as well as in batteries. Also, the next sixth category 2D layered material is HBN. So the hexagonal boron nitride. Also, synthesis is very easy. You can have take the boron nitride, then do the bath sonication, centrifugation, dry it, and then exfoliate it. So this is that simple. But you may need to do it multiple times because sometimes the HBN anode sheets may not get exfoliated. So these are some of the synthesis method which is shown, and also you can see that they are very good for the uh, supercapacitor applications. So almost 750 coulomb per gram, more than 750 coulomb per gram is the specific capacity achieved by this material, which shows its potential in the next generation supercapacitors. And the seventh member is, there are very less, maybe less than 5 reports in the literature, which is silicene based. So supercapacitor. So silicines are can be derived from calcium silicon disulfide. So once you exfoliate it, and you will get a single or some multi-layer silicines. So these silicines also found to be uh, very high performance in the for the charge storage. So these are also in the futuristic material, 2D material for the charge storage. And of course, I missed it, not missed it, because this already explored material, graphene. So graphene is the evergreen 2D layered material, the eighth material, which is good for supercapacitor applications. And this is one of our work which is patented, the US patent. So this is the vertically aligned graphene sheets on the carbon fiber, which is very highly flexible, and we had undergo 1000 bending cycles till it is the performance is not reduced. So this is a graphene also one of the, you can make composites with other battery type materials to make supercapacitor electrodes in the future. Now just talk about, so these are the future electric vehicles. We had structural supercapacitors or supercapacitors. So these are the one of the latest Volvo developed car, which is which is not in the market, but they demonstrated its performance. So the structural supercapacitor means we don't want the battery pack in the underneath. So this all body will be battery pack. So this is one of the method to enhance the performance of the car, and also it can reduce 15% of the total weight. So since our body itself become a energy storage device, we don't need of high amount of lithium ion batteries in the bottom, which is very unsafe. So these kind of devices will be the futuristic electric vehicles powered by the supercapacitor. And also one of the important thing is that there are people, they do research on recharging this battery with the braking energy. So that is also braking energy. It can convert it to again energy storage. So that is one of the another advantages of these kind of structural supercapacitor. So another application is the futuristic application is the textile supercapacitors. So these fields are not that much developed still in the, as I told, there are 55,000 articles published in the field of supercapacitor, but all these applications which I told, the materials development and strategies are still not explored, and there are more 55,000 papers can come in the same field in the future, because this is the only device that can give energy as well as power simultaneously. So this is the futuristic electronic wearables. You can have you can see that the current requirement for different powering devices, the which can be on body devices. So for smartwatch and microcontroller, joule heater, so you have different requirements. So based on that, you can redesign your supercapacitor and you can have it on your body. So that is the futuristic electronic wearables. You no need to, we no need to carry the mobile phones and charger always with us, and also we don't want to carry the battery pack with us. We can have a textile, we have our clothing itself will have a energy storage device. From there we just need a USB port to charge our devices. So this is the futuristic electronic wearables powered by the textile supercapacitors. And I would like to just explain some facts about publishing, because this is FDP program. So it's my experience as well as I got information from other people, from the other senior people. First is publishing a manuscript is not a luck. So this is basically, it is based on the quality. So we may, people may say that oh, maybe that people knows the editor very well, so the manuscript is easy. For we are not from that big group, so we cannot publish. No, that is absolutely wrong. So publishing manuscript is not of a luck, it is just because of quality. Second is cover letter. When we make a cover letter, it is not, should not be a copy paste of the abstract. The novelty statement should be very clearly mentioned in the cover letter. I am almost published more than 50 with as a corresponding author, so that's my experience. So always when we are not mentioning that novelty statement in the cover letter, the editor will just say it's a repetition of the work or it's just an improvement of the previous work. So we cannot, if you are not able to say it as a novelty, we cannot determine its publication. Second, next is supporting information is always helpful. We always give all the data in the main manuscript. So not only all the data, it is not mandatory that to give all the data in the supporting in the main manuscript. Give some unwanted data or some other extra data in the supporting information, which we can easy for the editor or the reviewers to see, because oh, okay, this is a quality work. So there are some more information. Maximize your information on your research work in the supporting information. That is always found to be helpful. And quality of the manuscript will be always considered at first during the first site itself. Otherwise it will go under, it will go for desk rejection. Desk rejection, it will go and from the editor itself, it will not go to reviewers. Then select the journal only based on the aims and the scope. So sometimes we want to submit that our research work on in a particular journal because it has high impact. So, but you need to, without seeing the aims and scope, we submit it. So it will get rejected. So what happens? It may take 10 days or 15 days to get rejected. So based on, sometimes you may see that the editor will say, this is not in the, not in the aims and scope of our journal. It may be more suitable in another journal. They may transfer it. So why do we waste for that much time? We can directly, we can send it if we know what is the aims and scope of the journal. Then next is, do not submit the manuscript in a journal where the quality is not adequate. Sometimes people, I felt that this submitting a manuscript into a high impact factor journal first, so that we will get comments, then we can submit into a lower impact factor journal by adding all the comments. That is wrong thinking. Okay, so once you submit number of papers, you will get it, a history will make, and history makes impact on your next publication. So even though you are publishing a high impact, good quality work, but still the editor may not consider because you have 30 papers already rejected. So 31st paper, if you submit a very high impact work, they will not consider it. So that is the history makes impact. So do not submit multiple lower quality manuscript in high impact factor journals. Also, do not submit multiple manuscript in one journal, even if one manuscript is under consideration after revision. Okay, we submitted in one manuscript in one journal, it got accepted. Similar way, we have another work also undergoing. So okay, so this is revision submitted, and most probably in a week it will get accepted. Okay, so the next paper also we'll submit in that one. No, because multiple manuscripts in a journal, it mostly they get automatically rejected, and they may not consider from the similar work from the same experimental work or the simulation work, whatever it is. Then next is add some references. Yeah, so before, when you want to submit multiple manuscript, what you should do is you need to first, that manuscript should be published in the journal. After revision it get accepted and it will get published, then you submit another manuscript, then it will go to the next flow. Otherwise, when one manuscript submit, okay, I have 5 manuscripts, you submit into the same journal, all 5 will get rejected next day. You can try it. So next is add some references from the submitting journal. That is also very important journal. Suppose you are submitting a paper to a journal where you are not citing that particular papers from that particular journal, then it is difficult, because you know that journals work with citations, so they need citation. Even we publish a paper in that journal, we also want to get citation. So always you need to add more number of papers from that journal. Not more number means, suppose you maybe at least 10% of papers you need to add from the same journal itself. Then some people say, oh, don't cite our own paper, so it will get a rejection. No, self citation is not a wrong thing if cited relevant to the discussion. If you are discussing about supercapacitor, and if I am citing my published paper of photocatalysis, that is wrong. But if I am citing my own paper when I am publishing a supercapacitor paper, then that is relevant to the discussion part. It is not treated as wrong. Okay, so it will also helps in your index and citations. And next is very important thing. Many kind of disputes happens due to crediting. So add proper credit to the contributors. So it is not like, okay, oh, he's my friend, so I don't want to put his name. No, I need to ask and to get permission from them. If they don't want to put their name, although they have contributed to the work, you need a clear-cut email evidence or some kind of evidence to stating that statements. So otherwise it will be a problem. And communicate with all others the submission of the manuscript. So before you submit any manuscript, you need to get a clear-cut communication with all the authors of the manuscript, because today's friend may be tomorrow's enemy, because these are different professions. Also, research is also a profession. We have today's friend may not like your growth, maybe tomorrow he become enemy and he may claim that, oh, I have contributed this work to this manuscript, so why, even though your manuscript got published in a high impact factor journal, it will undergo retraction process. And not only retraction process, it will ruin your name, it will spoil your future also. So this is very important. Many of the people, including professors in the universities or colleges, they feel that they can publish work with somebody, whoever they want. Oh, my student is depending on me for PhD, so I don't want to put her name for him or her in the manuscript, because I am the guide or the supervisor of the student. But student will get PhD degree or master's degree. Once they get their PhD degree, they will just try to email editor saying that I did not get my relevant credit to the paper. These are the evidences. They will show the email communications. Finally, will be in trouble. So it's very important to communicate with all the others and get the email communications saved. And last one is rebuttal to editor may be helpful if rejected unethically. If any paper which is rejected from any journal, and if we find that the points are not valid, we always can go to rebuttal. So among my papers, almost almost 10 percentage of papers I went for rebuttal to editor. So it works because you need to show it in a very polite manner that these things happened. These are the questions, and we have done this is work to the our work. And once the editor understands that this is sometimes the associate editors may not see the review comments because they are very most of the journals they are doing it for voluntary. It's not a paid one, but there are some paid publishers also where the editors and associate editors all get paid, but most of the high impact journals are unpaid, so they do voluntarily. Okay, so you need to understand they have other works. So among the time they are seeing, so if all the comments are not written properly or the answers are not written properly and also not politely, that also important, then the associate editor will get rejected immediately. So in that cases, if we feel that our work is still able to publish in that journal, we can go for a rebuttal to editor with a very polite language that may help for the publication. And that's all about my talk. Thank you. So welcome you from any questions from your side.
Thank you for your nice presentation, sir. Participants, you may ask your questions by unmute.
Sir, I have one question.
Yes.
Myself, Dr. Ajay Kumar Gupta. Sir, may you please go to slide number 21 or 22, please?
Yes. Yes.
Which plot is there, na? Nyquist plot. I think previous one. Previous one, sir. 21.
Oh, this one.
In the Nyquist plot A, B, and C, I could not understand one thing. First plot you have done in lithium hydroxide, and second is in sodium hydroxide, and third one is in potassium hydroxide, correct?
Yes, yes.
So I couldn't understand one thing. Why is semicircle area is increasing? It's so decrease actually.
Yeah. So you can go to the. We have proposed a theory for that in the paper. So if you, I think.
Because
I can show you. I can. Yeah. I don't know. I can show you the. I can tell you the.
Ajay Gupta, sir.
Yeah. Can you see my slide? Hello.
Yes, sir.
Yes, sir.
Yeah.
It is
Can you
visible,
see?
sir.
It is visible. Okay. So this is the figure number 7 of this paper. You can see this paper. So this is we explain based on the enthalpy of hydration. So different ions will have different hydration energy. Okay. So based on that, we have explained it. You can go to this paper, and if you still have question, you can contact me via email.
No, sir. Okay. My is still not solved. Lithium is the smallest ion, so its hydration power is very high. Since its hydration power is very high, ionic conductivity will be very less. And ionic conductivity is very less, so resistance, charge transfer resistance, which is reflected by the semicircle area, that should be very high in case of lithium hydroxide, because the concentration what you have taken for lithium hydroxide or sodium hydroxide or potassium hydroxide, concentration are same only 2 molar, 2 molar, 2 molar. So lithium is having the smallest size, so hydration is very high. Ionic conductivity will be very, very less. So resistance is very high. That is my point.
Okay, Dr. Ajay, we can discuss via email. So I may not be able to explain it now.
Okay, no problem, sir. Thank you.
Okay.
Thank you.
Yeah, you can contact me via mail. Yeah, we will discuss.
Yeah, please.
Participants were requested to put the queries in the chat box. If any query, put it in the chat box. It would be better to listen by all. Is there any queries from your end? It seems there is no question, sir. Thank you so much. Be for some time, and there should be a vote of thanks. Should be completed officially, sir. Please be. Thank you so much, sir.
Okay, okay, thank you.
Thank you so much, sir, for an informative presentation on supercapacitor technology. We appreciate the time you took to share us your expertise and insight with us. Your insights will surely be useful to other research scholars here who are interested in this field. Thank you so much, sir.
Okay, thank you. Once again, I am informing you when you have we have postdoctoral vacancies and brainful fellowship applications and PhD opportunities. So those who are interested, please contact us. We will help you in processing your applications. Okay, thank
So
you.
please be there. The function will be officially closed. I request our HOD mechanical, please offer a vote of thanks for this function, sir.
Okay, okay.
Sir, please, sir.
Thank you, sir. Very good afternoon to one and all present here. It's my esteemed honor and privilege to deliver the vote of thanks on this special occasion of Faculty Development Program on Advanced Functional Materials, Energy, Environment, and Sustainable Development, organized by Department of Physics in association with the Department of Mechanical Engineering, SRM Engineering College, from February 28th to March 6th, 2025. First and foremost, I extend my deepest gratitude to our Honorable Chairman of SRM Group of Institution, Trichy and Ramapuram campus, for his invaluable support and encouragement in organizing this FDP. A special word of thanks to our Chief Director of SRM Group of Institution, Trichy and Ramapuram campus, for his inspiring presidential address. Sir, your words have truly set the tone for this event, and we are grateful for your continuous support. Our heartfelt appreciation goes to our esteemed chief guest, Professor V. Subramanian, Department of Physics, IIT Chennai. Sir, your presence and insightful inaugural address have immensely enriched our knowledge and inspired us to explore new dimensions in the field of advanced functional materials. Dr. Dheerat Tirthagiri Jayaraman session on pulsed laser technology in electrocatalysis provided us with a deeper understanding of the latest advancement in laser assisted catalysis, highlighting its impact on energy conversion and sustainability. His expertise and research contribution have undoubtedly inspired us to explore this cutting-edge field further. Likewise, Dr. J.S. Chirusri session on two-dimensional layered material for futuristic super categories offered us fascinating glimpse into the potential of layered material in next-gen energy storage solution. His presentation was truly thought-provoking and has sparked new ideas for research and innovation in this domain. We are deeply grateful to both speakers from GN University, Republic of Korea, for taking the time to share their knowledge and for their engaging and insightful discussion. Your expertise has enriched our understanding and broadened our perspective. I would also like to express my sincere thanks to our respected principal, Dr. M. Sivakumar, and Vice Principal, Dr. C. Ramesh Kannan, for their unwavering support and constant motivation. Your guidance and has been instrumental in making this FDP a grand success. A special mention to the conveners of this FDP, Dr. K. Sakti Pandi, Dr. B. Seduraman, for their dedicated effort in meticulously planning and executing this program. Your commitment and hard work are truly commendable. I also take this opportunity to thank the co-convener, Dr. K. Venkatesan, Dr. A. Joseph Sagaya Kennedy, and Dr. S. Visveswaran for their relentless effort in ensuring the smooth execution of the event. A big thank you to the coordinators, Professor G. Prusothaman, Dr. Y. Bruce Lee, and Dr. P. Anita for their valuable contribution in organizing, managing the various aspects of the FDP. Our sincere appreciation to all the faculty members, participants, and distinguished guests who have joined us today. Your enthusiasm and keen interest in this FDP have made it a meaningful and enriching experience for all. Last but not least, I extend my gratitude to the organizing team, technical staff members, and volunteers whose begin this team effort have contributed significantly to the success of this program. Once again, thank you all for your presence and active participation. We hope this FDP has provided valuable insight and will lead to further advancement in research and teaching. Wishing you all continued success and innovation in your endeavors. Thank you all.
Thank you, sir. Now it's time to take a pause from our engaging discussions and enjoy some well deserved refreshment. I kindly request all the participants to arrive back sharply at 3 p.m. for our next session. The feedback link will be shared at the end of the afternoon session. Thank you.
Sir, thank you so much, sir, for
Thank you,
being with
sir.
us. Thank you, sir. So we'll keep in touch with you. So thank you. Thank you so much, all right, sir. Thank you, sir.